We use plastics for so many things. Water bottles, milk jugs, plastic bags to carry our groceries, forks, knives, coffee cup lids, even shopping carts. We use plastics for so many things. With so much plastic all around us, have you ever thought, what is a plastic? If we zoom in really close on a plastic, we would find that it looks like a chain of small units. One of these little units is called a monomer. Each of these little units, or monomers, are connected to other monomers, forming a long chain. This chain is called a polymer. Lots of these polymer chains get grouped together, sort of like spaghetti on a plate, and that makes up a plastic. Plastic polymers are usually made from oil, which is the same stuff that makes the gas we use in our cars. Well, how long does it take all of this plastic we use to break down? It takes 1,000 years or more for plastic to break down when we throw it away. What if we could engineer new materials that could break down easier? Well, fruits and vegetables break down or rot very easily when they're left out over time. In fact, they only take 3 to 4 weeks to break down when they're thrown away. What if we could make plastic out of fruits and vegetables? So today we're going to make potato plastic. We're going to make it in the lab here, but these are all ingredients that you can find in the grocery store and do this yourself at home. If you decide to do this at home, make sure you have an adult supervisor. This is our starch. This will be the backbone of our plastic. It is a molecule that's made up of chain of sugars, and you can get this from potatoes when you boil them. It's that milky white water. You can also find starch in corn, rice, or tapioca. We're going to use water to mix up all the ingredients and help loosen up all of those long starch chains to help make our plastic. Vinegar helps break the starch chains into smaller sizes, which make them more manageable while creating plastic. Glycerin helps make the chains of starch slip along each other, which help make the plastic material more flexible. We'll also need vegetable oil and food coloring just for our baking needs. Measure out 10 grams, or about 1 tablespoon, of potato starch. Add the starch to the beaker. To this we'll add 60 milliliters of tap water. Add 5 milliliters of vinegar. Add 5 milliliters of glycerin. It's very thick, so it might take a while to pour out. Add 3 drops of your favorite food coloring to make a very exciting plastic. To get this solution to turn into plastic, we're going to add heat. When you're doing this at home on a stove, be careful not to touch any hot surfaces or handle hot liquids directly. Stir the solution continuously on heat. As it starts to thicken, raise the heat from low to medium up to high. This might take some time, so consider asking a friend to help you stir. Once it finally thickens, allow the solution to boil on medium-high heat for another 5 minutes. You can see how the solution has darkened a lot and has become very thick and hard to move around. Allow the mixture to cool for a couple minutes so it's easy to handle. Grease the pans or molds that you'll use to scoop out your plastic with a little bit of oil. This will make it easy to remove the plastic once it's dry. Scoop the mixture into your mold and go ahead and spread it out as thin or thick as you want your final plastic to be. Stick the plates into the oven at 65 degrees Celsius or 150 degrees Fahrenheit for 1 to 2 hours. Now let's zoom in and take a look at what's happening to our polymer. So earlier we talked about an oil-based plastic, but here we've made our plastic from potato starch. The dried starch powder is a bundle of polymers. We add it to water to loosen up those bundles. Some of the starch polymer has branches on it, which makes it difficult to form a good plastic. We add vinegar to cut off those branches and make a linear polymer called amylose. If we just made plastic from this linear polymer amylose, we would get a very rigid plastic. We add glycerin to make the plastic more flexible. Now let's go see what it looks like when we take the plastic out of the oven. If you add less glycerin, you'll get a plastic that's somewhat hard and rigid. If you add more glycerin, you'll get a plastic that's more flexible and bendable. So depending on how much glycerin you add, you can create plastics depending on your needs.
Now, the key reason why we chose to use starch as our polymer is that it's biodegradable. That means natural organisms like bacteria are capable of breaking down the material into smaller parts. In this case, we take a polymer, our starch, and break it down into its monomer parts, in this case, simple sugars. Sugars are a vital energy source for all living organisms. As a result, many organisms, from bacteria to humans, have enzymes that break starch into simple sugars. Let's take a closer look at how this is done. The starch polymer is made up of chains of simple sugar monomers called glucose. The bonds that connect them are called glycosidic bonds. An enzyme called amylase helps break the sugars apart from each other by fitting between two monomers. A water molecule is absorbed in order to break the glycosidic bond between two monomers in a process called hydrolysis. Let's test whether our bioplastic is biodegradable. To do this in the lab, we'll need amylase enzyme, which will help break down the starch into simple sugars. This is actually a concentrated form of the same stuff you'll find in your own spit. Add the amylase enzyme to water, give the mixture a stir, and finally add the potato plastic to the mixture. We left this sample overnight, along with a control sample with just water. The control is there to see if water alone breaks up the sample. Notice how the plastic in the amylase breaks up? Here, let's take a closer look. This is what our plastic looked like before we biodegraded them. And this is what they look like after we biodegraded them. Again, notice how the sample that was in the amylase enzyme broke apart and degraded much faster than the plastic that was just in water. So we've just demonstrated that we can make a plastic that degrades in a matter of days, as opposed to thousands of years. So with a little bit of thought, it's possible for us to engineer better plastics for our planet.